Chapter 13 The Abstraction Address Spaces. In early days, building computer systems was easy. Why? You ask. Because users didn't expect much. It is those earned users with their expectation of ease of use, high performance, reliability, and etc. That really have led to all these headaches. Next time you meet one of those computer users, thank God them for all the problems that they have caused. Section 13.1 Early Systems. From the perspective of memory, early mechanisms didn't provide much of an instruction to users. Basically, the physical memory of the machine looked things like what you see in Figure 13.1, page 132. The OS was set of routines like a library, really, that sat in the memory. Starting in the physical address 0 in this example, and there would be one running program, a process, that are currently set in a physical memory. Starting in the physical memory address is 64 kilo in this example, and used the rest of the memory. There are a few illusions here, and some users didn't expect much from the OS. Life was unsure and easy for the OS developer in those days, wasn't it? Section 13.2 Multi-programming and time sharing. After a time, because machines were expensive, people began to share machines more effectively. That the era of multi-programming was born, in which multiple processes were ready to run at a given time, and the OS would switch between them. For example, when one decided to perform an I/O, doing so increased the effective utilization of the CPU. Such increase in efficiency were particularly important in those days where each machine cost hundreds of thousands or even millions of dollars, and you thought your Mac was expensive. Soon enough, however, people began demanding more of a mechanism, machines, and the era of time sharing was born. Specifically, many realized the limitation of the batch computing, particularly on the programmers themselves, who were tired of long and hence the inefficient, in, uh, ineffective programming development cycle. So the notion of interactivity becomes more important as many users might be concurrently using a machine as each waiting for or hoping for timely responses from their current executing tasks. So one way to implement time sharing would be to run one processor for a short while, giving it full access to all memory, figure 13.1, and then stop it and save all of this data to some kind of disk, including all of the physical memory, load some other process state, run it for a while, and thus implement some kind of cloud sharing of the machine. Unfortunately, this approach has a big problem. It is way too slow, particularly as memory grows. While saving and restoring register level slate, the PC, general purpose registers, and etc., is relatively fast. Saving the entire contents of memory to disk is brutally non-performant. Thus, what we later do is label processes in memory while switching between the home, allowing the US and implementing time sharing efficiently, as shown in Figure 13.2, page 133. In the diagram, there are the three processes A, B, and C, and each of them has a small part of the 512 kilobyte physical memory carved out for them. Assuming a single CPU and the OS chooses to run one of the processes, set A, as while the others, B and C, sit in the ready queue waiting to run. As time sharing becomes more popular, and you can probably get that the new demands were placed on the operating system, and particularly allowing the multiple programs to reside concurrently in memory makes the protection as important issue. You don't want a process to be able to read or worse, write some other process's memory. Figure 13.2 the three processes sharing memory. The 13.3 the address space. However, we have to keep those passive users in mind. and doing so requires the OS to create an easy-to-use abstraction of the physical memory. We call it abstraction, the address space, and it is the running program's view of memory in the system. Understanding this fundamental OS abstraction of the memory is key to understanding how memory is virtualized. The other space of this process contains all of the memory state of the running program. For example, the code of the program, the instruction have to live in memory somewhere, and thus they are in the address space. The program, while it is running, uses a stack to keep track of what is the function call chain as well as to allocate the local variables and path parameters and routine values and to and from the routines. Finally, the heap is used to dynamically allocate it and user-managed memory, such as they might just receive from a call to memload in C or new in an object-oriented language such as C++ or Java. Of course, there are other things in there too. For example, statically initialized variables. But for now, let us just assume those three components: code, stack, and heap. In the example in the figure 13.3, at page 134, we have a tiny address space, only 16 kilobytes. The program code lives at the top of the address space, starting the 0 in this example, and this is packed into the first 1k kilo of the address space. The code is static, and thus easier to place in memory. So what we can place in the top of the address space and know it won't need any more space as the program runs. Next, we have two regions of the address space, and we may grow and shrink while the program runs. Those are the heap at the top and the stack at the bottom. We place them like this because each wishes to be able to grow, and by putting them at opposing ends of the address space, we can allow such growth. They just have to grow in opposite direction. The heap does start just after the code at 1 kilobyte and grows downward, so that when a user gets more money via the memload, the stack starts in 16 kilobytes and grows upward, so that the user makes a user score. However, this placement to the stack and the heap is just inconvenient, just a convention. You could arrange the address space in different ways if you could like. We will see later. And we multiple threads coexist in an address space, and no nice way to divide the address space like this work anymore. Alas. Of course, when we describe the address space, what we are describing is an abstraction that OS is providing to running a program. The program really isn't memory, as physical address is 0 through the 16 kilobytes. Rather, it is loaded as some arbitrary physical addresses. Imagine examine the processes A and B and C in the figure 13.2, that you can see how each process is loaded into memory at different address and hence the problem. The crux: how to virtualize memory. How to the OS build the abstraction of private, potentially large address space for multiple learning process or sharing memory on top of a single physical memory. When the OS does this, we say the OS is virtualizing memory because the learning program thinks it is loaded into memory and a particular address, say 0, and has a potentially very large address space, say 30 bits or 16 bits, and the reality is quite different. When an example process A in figure 13.2 tried to perform a load and address 0, which we call it a virtual address, is somehow the OS in tandem with some hardware support. We will have to make sure the load does actually go to physical address 0, but less than a physical address is 320 kilobytes, where A is loaded into memory. This is the key to virtualization of the memory, which underlies every modern computer system in the world. The section 13.4 goals. Thus, we arrive at the job of the OS in this side note to virtualize memory. The OS will not virtualize memory, though it will do with the style to make sure the OS does so. We need some goals to guide us. We have seen these goals before we think of the introduction, and we'll see them again, that we are all certainly worth repeating. Our major goal of the virtual memory, VM, system is transparency. The OS should implement virtual memory in a way that is invisible to the learning program. Thus, the program should be aware of the fact the memory is virtualized. Rather, the program behaves as if it has its own private physical memory. Behind the scenes, the OS and hardware does all the work to multiplex memory among many different jobs and hence implemented the illusion. Another goal of the VM is inefficiency. The OS should strive to make the virtualization as efficient as possible, both in terms of time, that is not making the program run much more slowly, and spaces, that is not using the most time memory for extracting the needed to support virtualization, implemented timing efficient virtualization, and the OS will have to rely on the hardware support, including the hardware features such as TLBs, which we will learn about in the due course. Finally, a third VM goal is protection. The OS should make sure to protect processes from one another as well as the OSs are from processes. When a process performs a load, a store, or an instruction patch, it should not able to access or affect in any ways and memory content of any other process of the OS itself, that is anything outside each address space. Protecting thus enables us to deliver the property of isolation among the processes. Each process should be running in its own isolated cocoon, say from the leverages of the other faulty or even malicious processes. So in the next chapter, we will focus on our exploration on the basic mechanism system support. We also invest in some of the more relevant policies that you will encounter in operating systems, including how to manage free space and which pages to kick out of the memory when you run low on a space. In doing so, we will build up your understanding of how modern virtual memory system really works. The principle of the isolation. Isolation is a key principle to building reliable systems. If two the entities are properly isolated from one another, this implies that one can fail without affecting the others. Operating systems strive to the isolation processes from each other, and in this way prevent one from the harming the other. By using memory isolation, the US further ensures that learning programs cannot affect the operation of the understanding OS, so some modern OS takes the isolation even further. By whirling off pieces of the OS from the other pieces of the OS, such microkernels thus may provide greater reliability than physical monolithic kernel designs. 13.5 Summary. We have seen the introducing of a major OS subsystem, virtual memory. The VM system is responsible for providing the illusion of a large and sparse and private address space to each running program. Each virtual address space contains all of the program instructions and data, which can be referenced by the program via virtual addresses. The OS, with some serious hardware help, will take each of these virtual memory references and turn them into physical addresses, which can be presented to the physical memory in order to fetch or update the design information. The OS will provide this service for many processes at once, making sure to protect programs from one another, as well as protect like the OS, and the entire approach requires a great deal of mechanism. That is a lot of low-level machinery, as well as some critical parts to work. We will start from the bottom up, describing the critical mechanism first, and thus we proceed. Aside, every address you see is a virtual. Ever write a C program that prints out a pointer, the value you see, some large number, often printed in hexadecimal, is a virtual address. Even ever wonder where the code of your program is found? You can print that out too, and yes, if you can print it, it is also a virtual address. In fact, any address you can see in a programmer of a user level program is a virtual address. It's only the OS though it's tricky techniques of the virtualizing memory that knows where the physical memory of the machine these instruction and data values lie. So never forget, if you print out an addressing program, it's a virtual one, the illusion of how things are laid out in memory. Only the OS and the hardware know the real truth. Here's a little program va.c that they print out of the location of the main routine where code lives, the value of the heap allocated value returned from the memload and the location of integer on the stack. And when on the 64-bit Mac, and we get the following out. From this, you can see that a code comes first in the address into that heap, and the stack is all the way at the other end of this large virtual space. All of these addresses are virtual and will be translated by the OS and hardware in order to fetch values from their true physical location. References, and then the homework code. Okay.